graduate student at Grand Valley.
Yes.
And, well, Wayne, we're looking forward to this. Thank you.
Woo!
It's all yours.
Let me give myself a hand to myself first. I'll pump myself up. All right. So yeah. So if, I know most of the instructors here I've either had as teachers before, or I've known you guys since I was here. I was a student here from '96 till winter of '99. So it's been a while since I've been here, but I've been working here since March of 2009 again after I got laid off. But I like this. This is what I do. I love teaching math and tutoring math. And so, anyways, okay. And so, if you guys know me for a while, that I like to crack jokes. So, this is about the best Buddha picture that I can find on the internet. So I figure that's it. All right. So Buddha loves geometry, at least according to Japanese. Now, well, Japan's not the only country that that believes in Buddhism, but somehow this is what I found. What we're going to talk about is that we're going to talk about an object. It's called Sangaku, and that's the Japanese kanji for san and gaku. Literally means calculation, and this is for. I'm not quite sure what that is, and I couldn't find it, but in general that means you're going to calculate. So, and Sangaku, now what they are is that they're painted on wood pieces. With those wood pieces, now they're saying, well, you know what? We got those math problems we're going to paint on wood, and they brought it to temples to hang inside the temples. So, and literally what they do is they actually offer those to the Buddhist gods, and now Buddhists, there are tons of them. There are many gods. I mean, there's gods for your stove, there's God for your house, there's God for the land, there's God for lots of things. So they take those as offerings, and also they use those as kind of as a challenge for the people that goes to the temple. So, and there were most of them were found in the Edo period, between those times, and now in 1968. When the Edo period ends, that's when they started industrialization, because are destroyed as well. So far there are about 900 known that's left, and before there were lots and lots of it. So just a brief history, and that's what the Sangakus look like. So you got your temple, and there's some of the pieces in there, and I tried to get like a piece of two views together, but here are some of the questions, if you can see from the pictures, and these are the questions that they have for each of the pictures. And so I'm surprised that they actually last this long because it's paint, especially on wood. Figure they get weathered. And here's more. You notice the characters for the Sangaku right here, and you got your different shapes, the circles, fans, part of the circle, and there involves the triangles on this one, and your different squares. And this actually right here, this person actually wrote down the date of this is when this was painted, and that's that person's name. But I can't really read any of that stuff that's underneath there. I just can't read it. So, okay. So here's another better looking piece. So the more different types of problems. Okay. So this is the one that we're going to tackle today. So what you see here is you have a right triangle. I wasn't able to get that right angle sign in there, but you have a right triangle, and you have three circles. The big circle is tangent to all three sides. The middle circle is tangent to the base and the hypotenuse, and the big circle. And the small circle is tangent to both sides, and the middle circle. So that's what we're given. So, now, additional conditions. So we have the base is twice as long as its height. So I'm going to actually draw a better picture over here. Well, maybe not better. So 2x, here's x. And I have my circles. Sorry. Okay. And three circles of tangent. And so all the tangents we talked about. And the goal is that we need to find the radii of all three circles. And the additional topic after that is that suppose we keep the pattern going, what's the sum of the area of all the circles? So imagine we have more circles keep going. And so on, and so on. Okay. Now, before we can actually talk about finding the radius, I was stumped because I'm like, okay, this doesn't really tell me a whole lot. I have three circles with two measurements of 2x and x. There's no numbers whatsoever. So it's like, okay, what do I do? I mean, the most I can think, okay, well, I have a right triangle. So right triangle, what do you guys think first thing? If you have a right triangle. And also, if you have a distance of two sides, and you have a right triangle, the first thing you think of is what? Hypotenuse, so Pythagorean theorem, right? Okay, so I think about Pythagorean theorem, I'll say, all right, so a squared plus b squared equals c squared. So I have this. Okay, that's my hypotenuse. All right, now I look at it, well, it still doesn't really tell me a whole lot. Because I want to find the radius of all these things. But now I remember in geometry class, we actually talked about something called the incenter. The incenter of a triangle is that if you have a circle that is tangent to all three sides, which is what we have, that particular center is called the incenter. So basically, my given condition that I have a circle that's tangent to all three sides, so this right here is my incenter. And incenter, now, if you have an incenter, that means the radii from the incenter is also perpendicular to the sides of the triangle. Let me get a different color. Okay, so this is what I have. So I was thinking on the line of this. Okay. This took me 3 hours to figure it out. I was staring at it for a while, and then I realized, oh, okay, so now if I want to, now once I have all the sides, and I know this, well, at least I can find the area of the triangle, right? Base times height times divided by 2. Okay, but now the thing is, now I realize, well, if I have the radius coming from the incenter, I could do this. And this is what happens over here. I have just split this right triangle into 3 different triangles. From ABO, BOC, and COA. Those are my 3 triangles. And since the radii, they're all perpendicular to the base, to each side, so what I could do is I can find the area of ABO plus the area of BOC plus the area of AOC, then that should be the same as 1/2 times x times 2x. Oops, dropped. And this is exactly what I did. So here is some of my descriptions. Okay, so. And I want to apologize ahead of time. I did this in Office 2010, and when we did it again in 2007, some of the functions got lost. So and I couldn't fix it. I can't fix the slide for some odd reason. So this is basically what I did. I first found the area of each. So I have 1/2 x times r1 plus 1/2 2x times r1 and plus 1/2 the hypotenuse, the base, times another r1. So r1x square root of 5. And that's going to equal to my area of 1/2 times the base times height. 2x squared. Okay. And from here, we notice we got a bunch of halves for each term and the x's in each term. So we can basically just cross all those out. And in the result is that we have r1 times 1 plus 2 plus square root of 5 equal to 2x. So in this case, dividing the 3 plus square root of 5 on both sides, we have r1 is 2x over 3 plus square root of 5. Okay. So any questions so far? So pretty straightforward, right? Yeah. Okay, so now, this is where the fun begins. Oh yeah, so, okay. So now the problem is, well, okay, so I know this right here, now we have all the values for the R1s. Now how am I going to figure out R2? Well, what we could do here is I notice, well, guess what? From the in-center of O to drop it straight down the R1 to this point, and if I go all the way across, what happened here is you now have a right triangle that contains R2 and eventually R3. So now learning, remember from trig, we can use similar triangles. So before we find R2, now the problem is we really don't know that all the centers lay on the same line. You just don't know. You can't assume. But what we could do here is that, well, if you think with me right here, if I drop a vertical line right here where the R2, on the edge of R2, and same thing for R3, what happened here is I have similar triangles. Because if you drop a vertical line, these two lines are parallel. So therefore, and they share the two sides in the same angle. So they're similar. So therefore, with more work, obviously, but then we can say that the centers will be laying on the same line as well. So therefore, we can use, so the similar triangle argument will be valid. Okay? So that's basically what we're looking at right now. Okay, so this is what we have right here. This is R2. R1 we said is 2x over 3 plus square root of 5. All right, so now the problem is, well, I need to figure out what this side is and what, let me see, I'm sorry. I need to figure out what this side is and what this side is. Not enough information, right? Looks like it, but we'll make it work. So, okay. Yeah, see, this is what happens. Now the thing is, okay, so originally, now remember we said the base of the big triangle is 2x, correct? So since this is R1 right here, so that means the distance from this point to this point is also R1. So I could find from this point to this point by subtracting it from 2x. And that's exactly what I will do as soon as I get this to work. There you go. So we take a 2x minus 2x over 3 plus square root of 5. And we have this distance right here. So here's that. Now, okay, and so from here, again, we have a right triangle. So Pythagorean theorem once more, we can find out the hypotenuse of this length right here. Which is and so we jump through all the hoops doing this. There you go. So a squared plus b squared equals c squared, and we did all our work. And so we arrived at the hypotenuse is now 2x square root of 10 plus 4 square root of 5 divided by 3 plus square root of 5. I kind of like this. Notice you have the 3 plus square root of 5 all over the place, which is really cool. Okay, so, all right, so now the biggest problem is that, well, what's going to happen here? If you remember from this picture, notice from the first center and the second center, you have two, it's basically one line segment made up with what? R1 and R2, right? So what we're going to have to do here is that we're going to have to subtract that out. So that means I need to take, to figure out this distance, I have to take my newly found hypotenuse minus R1 and minus R2. So and this is where it gets really messy. Bam. Yes. What I did here was that, well, I actually, so right here on the left-hand side on the way top, that's where you have the hypotenuse minus R1 and minus R2. And so that's this segment right here. So basically what I did is I have two triangles, again, using similar triangles. Okay, so basically I use similar triangles and use my proportion. So here's my original hypotenuse divided by the R1 equal to the shorter hypotenuse divided by R2. And what I did first thing here is that I actually took care of the right-hand side first since they have the same denominator. And then I simplified it down to this. Then from here I cross multiply. So. And once we cross multiply, what we could do here is that, well, if you remember for some of the algebra students, right? You have all the, especially in trig, you have x's on one side with a really ugly coefficient. So we bring all the variables on one side, we factor it out. So I move this R2 over here, factor out the R2, then divided by the rest. So now we have this R2. This took me a while because I'm decent in algebra, but I'm still not perfect. Nobody can be perfect. So I made a few mistakes in the middle while I'm multiplying. And one mistake cost me because I think I made a mistake somewhere around, I think around here when I was multiplying stuff. And it was bad. It turned out, and I think I ended up getting a negative number for radius. and that obviously didn't work. So, okay. So now the thing is, all right, so, and from here I was like, okay, well, you know, if you look at this, do you see anything good in R2? Something that looks at least familiar? That's your R1, isn't it? Okay, so that means basically we're saying here R2 is R1 times whatever that is. So we have the one's a minus 1, and this is the same thing, plus 1. So, okay, so I found that, and I was like, all right, you know, my imagination is kind of okay, you know. Since these follow some kind of pattern, so hopefully we have a pattern of some sort, right? So I was thinking, well, if this is R1 and R2 is basically R1 times this, so automatically you think what? R3 will be what? You multiply by it again, right? Right, but of course, we can't just assume since we're mathematicians. So what we're going to do here is we're going to do this. So finding R3. And R3 is going to be similar techniques as well. Because what happened here is, so now if I'm looking at my R2 and R3, so again, this is R2 and R3. So we're going to basically apply the same technique how I did over here. And that is going to be very long. It's just because the number is so ugly and it got huge really, really quick. And so same idea, right? I take my result and minus R2 and R3, divide by R3, so there is my smaller triangle right here. And on the left, that's actually using the bigger triangle from here to here. So, okay. So right here again, we're gonna cross multiply. All right. And actually, I believe I skipped a step because what happened here, if you notice on the left, again, they have the same denominator, correct? So what we could do is we could take care of that right there. So it's less work. So if you cross multiply, then we have this big globs of numbers and expressions. And so we took care of that. And simplify more, we have this. And okay, so we multiply, and then so what happened here is I divide this on this parentheses of a fraction on both sides, and luckily some of them do cross out, but it actually took me for a while because I'm decent at factoring, but not with anything that involves radicals. Especially with radicals now, because you're going to end up having, say, if you multiply this, right, you have 10 plus 16 times 5, and it's not like your normal x and y's. It's just harder to do. And it actually took me a while to realize, oh, by the way, when I simplify all this, I actually get this back. And guess what? Pattern follows. So, and from here, I actually did more work to calculate what R4 is, but R4 is, it gets worse. It gets worse and worse every time you do it. Okay. So basically, so far what we found is that, well, we know R1 is 2x over 3 plus square root of 5. And we said R2 is basically 2x plus 3 plus square root of 5 times square root of 10 minus 4 square root of 5 minus 1 over square root of 10 minus 4 times square root of 5 plus 1. Oh, I'm sorry. It's plus. Thank you. Couldn't see it. Thank you very much. So, and that just means R3, then we found that we basically is, we just keep going. Okay. All right. So that means if you do R3, we're basically just we're gonna keep the same 2x plus 3 plus square root of 5, and next one is 1, 2. Then we're gonna do the same thing for. So R4 is just 1 less. So we're gonna keep going our pattern. Okay. So any questions about how we come up with the R1, R2, and R3? And if it doesn't make sense, please let me know, and I'll do my best to explain for you. Okay. Okay, so now the thing is, well, if you look at this now, it seems like basically we're multiplying the radius by the same thing over and over again, right? So if you're in Calc 2, or if you're in 110, you guys remember talking about series, right? Infinite series. So if you're multiplying the same number over and over again, it sounds like a geometric series to me, right? So this is what we're going to do then. So we're going to think this is an infinite series. We're looking for the area of all the circles. And so this is what we have. So basically, my first circle is going to be pi times r1 squared, pi times r2 squared. We're going to just keep thinking that way. Then now, but the thing is, we realize that we made the connection saying that, well, r2, r3, and r4, they're basically just r1 multiplied by some number. And so this is what we're going to do. First thing first, and we'll factor that pi out, because since there's a pi there. Then what we're going to do here is that, well, we're going to rewrite the r2 and r3 and r4 in terms of r1. Because we know this, then we have all that fun stuff. So that means R2, I rewrote it as in terms of R1, just like what we had over here. And same thing for R3 as well, and so on. Now, since we have everything in terms of R1, especially R1 squared, what I could do is I can factor that out from every single term. Right? So factor everything out, so I now have 1 plus this square plus now this raised to the 4th power. Okay, and now the thing is, if you look at it now, what happened here is, well, you have this parentheses, you have a 1 plus this quantity squared plus this quantity to the 4th. Doesn't really look like a geometric series. But however, if you actually multiply everything out, what you have here is that, or you could think of this way as you're multiplying by what your R is. Just now to refresh everybody's memory on the geometric series before I do that. It will be so this is our geometric series. And so what we could do here is that if we can treat our R as, in this case, R as the square of, sorry, this is going to be our R in this case. If you notice, we're multiplying by this at every single time. And now the only problem is now, if I want to find the sum of this, the R has to be less than 1, correct? So if you calculate, I actually calculate this, and this is indeed less than 1, because if you look at it, you have the same value, but 1 is minus 1, 1 is bigger than 1. So therefore, the numerator has to be smaller than the denominator. Therefore, the whole fraction is less than 1. So when you square, R has to be less than 1. You don't have a choice. So then what we could do is, there is a formula for finding the sum of a geometric series, especially for infinite ones. It's called A over 1 minus R, where A is your first term. So that means in our case, what we could do is, our first term is going to be 1. I'm going to do 1 minus 1 over 1 minus R, which in this case, we have this big fraction right here. As I've shown, here it is. Okay. So finally, we have that. So this beautiful fraction of 11 plus 4 square root of 5 plus 2 times 10 plus 4 times square root of 5 divided by the quantity of 4 times square root of 10 plus 4 times square root of 5 is the area, is the sum of the area of all the circles in this particular triangle. Well, of course, then at least that's what for the radius. Then once you actually calculate out the pi times r1 squares, it depends on what the x value is, and then this will give you the actual sum of the entire triangle, entire circle in this particular triangle. So it really took me a while, and I stumbled on this, many times just because the algebra was just, it was just a lot of algebra and I couldn't do it in the first time. It took me probably about, collectively maybe about between 10 and 15 hours and just do a little bit at a time because I can't focus. I just can't focus that long. Yeah. So any questions?
Was this one of the ones that was actually found as a painting?
That one, actually, I have no way of verifying it. So they don't really have like a database of what's found and what's not.
And just by the looks of the things that you were showing me, it looked like they had a lot of problems that involve circles.
Yes, a lot of circles, a lot of triangles, just like different shapes. They have just even some that involve squares or rectangles. They're just throwing them on. There were a lot of them. So yes, anything else? Yes, Mr. Rich.
So these date back to 1600s?
Yeah, 1600s and on, yes.
Do you have any idea how Japanese at that time would have solved these? Are they using, what you're all seeing here is modern algebraic notation.
Right.
Now, at the end of that period, that existed in Europe. I don't know what the Japanese had. At the beginning of that period, the modern algebraic notation didn't exist anywhere. So,
right.
do you have any idea what they actually did to solve these?
I actually tried to look into it to see if there was some kind of like a solution to it, like how they would present a solution, but I was not able to find one. So, but I think, I can read some of the Japanese characters, at least according to some of those on tablets, and so I would assume that they will probably have everything written, maybe not necessarily in terms of X or Y, but maybe they're just saying this is something in Japanese. So this, and just use that instead of the X and Y notation or R and A that we use. So, and this is actually really interesting because I mean Japan is they're a country on they're surrounded by the sea, so I don't think they're gonna have a whole lot of communication with the guys up over in Europe. So stuff that, I mean, a lot of times, they're all, I mean, not even just in Asia and Europe, but even just within the countries, a lot of times you have mathematicians, they're doing the same thing, but independently. Like Newton and Leibniz, calculus. Yes, sorry, Mr. Harris.
Did you have to look for that constant anywhere on the internet, see if that constant shows up anyplace else?
I did not. I actually did not. But it's just, yeah, the thing is, all of a sudden, then we have this. It just kind of shows up all of a sudden. So, yes, sir.
Would you say that these questions would have been posed to our equivalent of graduate level or high school level? Or
This one? Well, the thing is, I don't think the idea of the geometry now, I think that's a high school level geometry because I don't think in-center that's not something that's required graduate level. I mean, I'm pretty sure that I've heard that before in the geometry class, but I think the algebra isn't necessarily hard, it's just long and has a lot of terms. It just gets messy. So I think high schoolers can do it. But maybe you just need to actually, buckle down and just look at it several times instead of just try to do everything in one shot. Because I certainly couldn't do it. Yeah.
But now these things were in temples, though, right?
Yes.
So it was more of a meditative kind of thing? Or, I mean, it's not posed to students.
Right. That's why they're saying they were putting this in the temple as an offering to gods. So that's why I did not know Buddha likes geometry. I really didn't know. So, yes, Mr. Warrington.
Could you give us some other examples of what was on the wall other than this one?
Yeah, they had some, like even some of the examples. I wonder if I can find it. Now, I wasn't able to find. There were a few others, but I didn't look it up. But I believe if I go back to this slide right here, I think this will probably be a good one to look at. Yeah. So then you have like a fan shape with the similar circles and yeah, and some of these writings, just their language. I mean, I can read the characters, but the language is a little bit old, so I'm not exactly understand what they're talking about. So yeah, it mentioned about the different circles that you have and the fan shape, but I couldn't make out what they're saying. So if I can find maybe like a translation, we can probably do it. Anything else? Yes, I think.
So these were fun inside of templates. Were they kind of, if you come to the template, you come and do these for fun, or was this something that, it's required of you before you enter or exit the temple? Was it a lesson? If you're a Buddhist, things you can solve the circles. You sit there for, 45 days.
If you cannot do these math problems, you're excommunicated from the Buddha temple. No. Actually, they said this is actually part of for fun as well. So.
It's cruel fun.
I don't know. Hey, whatever floats your boat. Okay. Anything else? Yes, sir.
So, Wayne, your curiosity is a mathematician. What happens if you change the 2x to mx?
2x to mx. So that means I get to.
I just wondered if you explored that.
No, I have not actually.
Okay.
Well, I could probably do it.
This next week.
Yeah, I know. I'm sure it's doable. I mean, it's just that there's some calculations going to have to be adjusted where that 2 becomes an m, and we're just going to have a lot more terms.
You wonder what the common ratio is going to be and how it relates to the one that you found, and it's an interesting problem.
This thing really took me for a while because when Dr. Novani and Grand Valley first handed out this problem, I was like, there is no way. How do you even do this? Are you kidding me? But after doing a little bit digging, actually a lot of digging, and throughout old information found earlier weeks in the class, and we're like, oh yeah, it's just everything just kind of leads from one to another. So I mean, yeah, but I think this pretty much this goes for with all the math classes as well. I think I'm taking number theories right now, and a lot of stuff we're doing right now is all definition, prior definitions, and yeah. Okay, any other questions? All right, then thank you very much for coming.